So, hello, my name is Meredydd, and I am here to talk about a project called Anvil, which is a framework for building full-stack web applications entirely in Python. So, Anvil is a framework that runs Python in the web browser, Python on the server. It even has a Python user interface toolkit. So I really do mean entirely in Python. And what we're going to talk about today is the rationale behind building a toolkit like this. I'm going to walk you show it to you in practice, and then we're going to go behind the scenes, under the hood, and show you how a bunch of it is actually done. But first, it's a reasonable. The reasonable question is, why do we care about any of this? And the real answer is that the web is not a very developer-friendly platform to program for. In fact, I'd go so far as to call it developer hostile. And the real reason is because there are so many layers. So if you think about the web from the perspective, let's say, of a piece of data. So if you're building a traditional web application, your data is probably going to start as data in a database accessed by writing SQL queries, but it's not going to stay there. You're going to turn around and immediately transform it into objects in your server-side programming language, probably Python objects in present company, accessed by methods and attributes. And then you're not going to leave them there, because what you're going to do is turn around and immediately render those as JSON over HTTP endpoints with a very large number of nouns and a curiously limited set of verbs: get, post, put, delete. But of course, on the other end of that HTTP request is a JavaScript program that is reassembling that data into objects in JavaScript with their own set of methods and their own set of attributes, and is then transforming those into HTML DOM with its own idiosyncratic API, and then into pixels to actually show to the user's eyeballs. Now, that is a lot of different representations. And indeed, most of the day-to-day work of web development is transforming data between these adjacent representations. And that is tedious and repetitive. And because it is tedious and repetitive, we try to automate it. And that just attracts the wrong sort of magic. What do I mean by the wrong sort of magic? Well, I'll explain by taking a completely unfair pot shot at SQLAlchemy. So if you're not familiar with it, SQLAlchemy is a library for automating the translation between SQL database queries and rows in SQL database and Python objects. So instead of writing queries in SQL like this, with SQLAlchemy, you can write Python expressions like this. Query, book, filter, book.price is less than 20. That's nice. But, of course, the process that transforms that Python expression into SQL you can run against a database is black magic. We are talking meta-classes. We are talking innocent Python operators overloaded to do something completely different to what they normally do. And this will bite you if you start treating book.price is less than 20 as if it were the numerical comparison it looks like. You're going to come unstuck. It's actually an overloaded operator generating weird internal objects that's used to render a program in a different programming language. But in exchange for this complexity, you do get to write faster code, and you don't have to generate SQL. Everything stays as Python objects. So you get a speed productivity increase at the expense of having to understand Python and understand SQL and understand how it is that SQLAlchemy does the transformation, which is probably an acceptable cost if you do this once. But if you did it at every level of this stack, then you'd be in for a bad day. And of course, that's exactly what we do. We don't leave it just at ORMs, converting database rows into Python objects. We've got REST frameworks helping us render those objects over HTTP. We've got JavaScript frameworks like Angular's resources on the other end, helping us to reassemble that into JavaScript objects. We've got templating systems like React, helping us render that into HTML DOM. We've got CSS frameworks like Bootstrap, helping us render those into pixels. And every one of those is the wrong sort of magic. Like SQLAlchemy, they can be powerful tools, but in order to use them well, you need to understand the representation it's transforming from, the representation it's transforming to, and quite a lot of detail about how it does the transformation. And you end up needing to know everything in blue here and everything in orange. We're Pythonistas here. How does that stack up against PEP 20, the Zen of Python? You've heard this series of phrases, philosophies of Python as a language. Here's a famous one. Simple is better than complex. Was what I just described to you a simple system? No, it was not. Here's another famous one. If the implementation is hard to explain, it's a bad idea. Well, the inside of web frameworks is famously gnarly. The inside of ORMs is just as gnarly. If you're having to explain something that includes meta classes, you're probably on thin ice. Oh, here's a famous one. There should be one and preferably only one obvious way to do it. Ouch. So the web is way too complex, requires us to know way too much just to get anything running at all, and is thoroughly unPythonic. How could we do better? Well, obviously, I am here because I am presenting a stab at an answer. And what we thought when looking at this stack is that you could build the best web framework in the world. But if you just swapped it out and tried to replace Django, it wouldn't help. The problem here comes not from the design of these orange boxes, it's that there are so many translations to be done. And so as long as you're slotting into this world, then you're going to be maybe an incremental improvement on what went on before, but all the developers who use you are still going to have to grapple with all of this complexity. So what we thought of with Anvil was, well, why not lose all of this and replace the entire stack with one representation? And the representation we chose was Python objects. So instead of having to translate between these 6 different representations, we built a UI toolkit that allows you to represent the state of your GUI as Python objects. We built a framework that runs Python code in the web browser. So now you can drive your UI by manipulating Python objects, rather than by generating source code in one programming language to be interpreted by another programming language into pixels. You just drive a Python object. Python on the server, obviously. But if you've got Python running in the browser and Python running in the server, you don't need to mash all your data into JSON anymore. You could just have a function call. We even built a Python native database so that rows in the database are shaped like Python objects. And so you can take a record all the way from your database to your user interface without changing its representation. And so you get to omit basically most of the day-to-day work of web development, and you get to build something much more quickly and much more easily. All right, so that was in theory. Let me show you what that looks like in practice. Okay, so right now, what you are looking at is the Anvil editor. And I'm going to show you how to build an application with Anvil by building one in front of you. So I've just hit create an application. I'm choosing a theme. I'm creating, there we go, creating a new application. And here I am inside the Anvil editor. This here is a web page. And this is a toolbox of things I can put onto my web page. So if I want to put, for example, a title on my page, I take a label component and I drag and drop it into the title bar. And now I can select it, I can edit its properties, I can change its text to say, hello, Python, Python. Okay. So that was pretty straightforward. Let's do something a little bit more interactive. So I'm going to build a Hello World application that is going to prompt the user to enter their name and then greet them by name. So what I'm going to do is I'm going to put a card on here. I'm going to put a label on it to prompt the user to enter their name. I'm going to add a text box so they can answer that question. I'm going to call it name box. So everything in Anvil has a variable name, so we can access it from code. I'm going to put a button so they can for them to click when they've answered that question. We'll say hello, like a little bit more prominent, and you can see what's going to happen here. The user is going to put their name into the box, click the button, and then we are going to display a greeting. So the final thing we need is to have a label to display that message on. I'm going to call it message label. And we can change some more properties here. So we can make the text centered, we can make the font big, and so on. So I've just built a UI. And obviously that was a lot faster than it would have been with HTML and CSS. But the really cool thing is this is backed entirely by Python. So if I double click this button, I am now editing the Python code that runs when that button gets clicked. And you can see all the things that I dragged and dropped onto my page are available as objects in my Python code. So if I want to change the text on this message label based on the text that went into the name box, I can go self.messagelabel.text equals hello namebox.text. And that's it. I run it. So get rid of that. Okay, so we have just built an actual interactive web app entirely in Python. It's time to put it on the web. So I'm going to hit publish here. I'm going to add a URL. So this is a private URL, like a Google Docs sharing link. Let's make it a little bit, make a public link, make it a little bit easier to type. I'm going to go with hello sfpython.anvil.app. Python sf, okay. Right, that's it. It's live on the internet. So you can go to right now, python-sf.anvil.app, and the app that I've just built is live. Someone stick it in the chat. So we just built and deployed a web application entirely in Python. Now that was pretty neat, but so far everything we've been doing has been running in the browser. This Python code gets compiled to JavaScript and runs in your browser when you open the app, which is nice for snappy interactive applications. But of course, any serious application is going to need some server-side code as well. So let's add a server module to our app. This is a Python module on the server. This is a perfectly ordinary Python module, in fact, and this is a perfectly ordinary Python function. What I can do here is I can decorate this function with anvil.server.callable. And what that says is that this function running on the server, we should be able to call it from the browser. So if we go back to our browser code, here's the function that runs when the button's clicked, as well as updating the UI, we can anvil.server.call the say hello function we just defined. We see it wants a name parameter, so we could give it the text from the name box. And now, if I run this, you can see that we've got something in the logs. If we go into the logs, we can see that message was printed, and that was what we're seeing there is a print statement running on the server, driven by this UI we've built entirely in Python. And now we are properly in business, because of course there are going to be limits to what you can write here. This is being compiled to JavaScript. You're not going to be able to open files. There's a whole bunch of modules you're not going to be able to use. But once you're on the server, this is a full CPython environment. So you want to talk to a database, that's fine. Import scikit-pg2, go. You want to do some statistics, import scipy, go. You want to do some machine learning, import PyTorch, knock yourself out. In practice, the first thing everybody wants is a database. So we actually have a built-in database called the Data Tables service. So this is backed by Postgres, so you can stick gigabytes of data into this thing if you want to. I'm going to be a little bit less ambitious. I'm going to make a single table for recording the names of visitors. Okay, so there we go. It's going to have, sorry, clear some of this stuff up. It's going to have a text column to store the name, and then it's going to have a date and time column to store when that name was entered. And that's it. I've created my database. This table is called apptables.visitors, and it's accessible from my code in exactly the same way that those buttons and text boxes were. So on the server, as well as printing that message, I can take apptables.visitors and I can add a row to it, and I can fill in the name column with the name that was passed in. I can fill in the when column with datetime.now, which I'll need to import. Okay, and now if I run this, with a couple of different names, and let's minimize that. Okay, let's go back to our table. You can see that we've actually got a couple of rows in our database already. So we've just built a base-backed web application entirely in Python, and I remind you that this is live on the web right now. There's a link in the chat, and you can absolutely stick your name in it. Okay, I want to show you one more thing before we go behind the scenes, which is how we display some data from the database on the UI. Now, as I've just said, that's that application is live on the internet, and we don't want to disturb people who do that. So let's create a branch to work on this. Oh, let's make that commit. Okay, and let's create a branch. Display. Okay, switch to that branch. Right, so we want to display the contents of the visitors table on the UI. So the first thing we need to do is to be able to get that data from the server. That's no problem. We make a callable function, get visitors, and it returns apptables.visitors.search, which is a iterator over every row in that database. We could constrain it and search for certain things, or we could get every row, which is what we want this time. And now we want to go to our UI and display that information. So the first thing we want is UI to display it on. So I'll have another card. On that card, I will add a data grid. This data grid is going to have a couple of columns. It's going to have a column for the name, which is going to pull the name key out of everything in it. It's going to have a column for when, which is going to pull the when key. And we don't need a third column. And we can do things like, we can adjust the width of that, make it look nice. OK, now inside this data grid, we have something, a component called a repeating panel. And what that does is it has a property called items. And we can set this to anything that Python can iterate over. And it will instantiate this chunk of user interface, which is actually, this is a separate class. It will instantiate for every element in that iterable object. So all we need to do is we go to the code in our constructor. When this is loaded, we set the items of that repeating panel to the return value of get visitors. Now we can run it, and you can see we are displaying everything in that database. Good to see some audience participation. So we've built a database-backed web application a full stack database-backed web application with nothing but Python, and we've deployed it. And there's only one thing I want to do before we go into how on earth that all worked, which is that this is kind of ugly. Yeah, you can sort of see what's happened here. We've taken a datetime object and then we've called stir on it, and it's producing the rather human unfriendly stuff. So let's go in and fix that. So I'm going to display this a little bit more. What I'm going to do is I'm going to edit this UI template, and instead of the default handling for the when column, I'm going to put a label into this slot. And then for this label, I am going to add a data binding. And what that says is it sets the text property of this label to this Python expression. And self.item here is a row from the visitors table. Remember, these rows are Python objects. I can use dictionary style lookup to get some column values from it. In this case, the when column, which is a date time. Of course, that's a Python date time object, which means I can just call stir of time at it. Boom. All right, so let's run this. And now you can see we've got some nicely formatted data. Oh yes, somebody's testing the emoji support. Of course, everything's Unicode, supports Unicode everywhere. This is Python. All right, so I think this application is now working. So let's merge these changes back into master, because this URL is pointing at the master branch. And so now we've merged those changes back. You can go to hello-python.sf.anvil.app and see everything I've just built. So that was a full stack web application built entirely in Python. Let's go behind the scenes and see how all that worked. And obviously, this is going to be a whistle-stop tour. There is an awful lot to Anvil. But don't worry, if I miss anything, the framework is open source, so you can just check it out on GitHub and find out anything that I didn't tell you already. OK, so we're going to talk about a few of the things that you just saw, starting with possibly the most obvious, which is compiling Python to JavaScript. Because what you saw is me just building client-side code in Python and then running it in a web browser. And web browsers don't understand JavaScript. Sorry, they barely understand JavaScript. They certainly don't understand Python. And so we need to translate that Python into something they do understand. And for this, we use an open source project called Sculpt, which is a Python to JavaScript compiler. You feed it a Python expression, it will produce some JavaScript code that does the same thing. you give it a Python function. It will produce, honestly, the ugliest JavaScript function you have ever seen, but it will have the same effect as that Python code. Now, this is great, and it was already available at the time we started Anvil. But back when we were first building this, we had a problem, which is that JavaScript is, in its infinite wisdom, a 100% non-blocking language. Every JavaScript function must finish executing in order for the browser to be alive and be able to continue interacting. And this is a problem because Python is idiomatically a blocking language. So we wanted to build APIs that looked a little bit like this. Here I am querying a database, and then I'm doing some computation based on the results, and I'm expecting that to block while it gets something from the database for me. Here's how you'd write that in JavaScript. 1, 2, 3 nested callbacks. And sure, these days you would be using promises or async await, but the fact is that promises and async await are another example of that sort of magic where you need to actually know how it works in order to use it effectively. You need to understand that promises are basically callbacks in order to use promises well. And you need to understand that async await is basically syntactic sugar for promises before you can use async await effectively. So you really do have to be able to deal with this complexity to do any of this at all. But conveniently, we had a Python to JavaScript compiler. Why not try and turn that into that programmatically? So we grabbed the source code from GitHub and start exploring. It turns out that Sculpt has a pretty classic compiler architecture based, unsurprisingly, on CPython. So here's how it works. You feed it a string that contains some Python source code. The first thing it does is it will tokenize that string. So it will split that up into substrings that are relevant to Python. So here we have, you can see these are useful chunkings for Python. By the way, all these JavaScript file names are the file names in the Sculpt source tree if anyone's following along at home. So you've tokenized this thing, and then you will feed those tokens to a parser, which will generate something called an abstract syntax tree. And that is a tree of operations as we think of them in Python. So, for example, that code is represented in an AST as, well, it's an assignment. And on the left-hand side of that assignment is a variable named result. And on the right-hand side is a function call, calling a function named f with an argument with the numerical constant 42. And once we have assembled this tree, then we have a compiler that can walk over this tree, spitting out JavaScript. Now, obviously, if we want to translate blocking Python to non-blocking JavaScript, this is the part that we're going to have to modify. So what we did was we invented a new sort of return type. See, remember, one Python function produces one JavaScript function, and we didn't want to mess too much with that. But a JavaScript function has to return. So we created a new return type that says, actually, I'm returning, but I'm not done yet. I'm just blocking. And we call that a suspension. And so if you have an AST like that, like this, we generate JavaScript code a bit like this. So we call the function f with the argument 42, and then we check whether the return value was one of these suspension objects. And if it was, then we save our own execution state as another suspension and return that. Here's how that looks like in practice. So here we have a function that's then going and getting the database, and then doing some computation on the result. So here's the call stack. We have the Anvil runtime, which is handling, our UI, our button clicks. That's called button one click. That's called the get, and that's called the get method, and that's gone and accessed the database. And of course, the database blocks. So that returns a suspension. The get method realizes it's been given a suspension, so it saves its computation state. It saves the value of its local variables. It saves the temporaries, any halfway completed expressions. It saves where it is in the function, and then it stores all that information in a suspension object that also refers to the original one. And it returns that to button one click, which does the same thing. It realizes it's been given a suspension, it saves its locals, saves its temporaries, saves where it is in the function, and returns a suspension to the runtime, which then sits on it and goes, okay, well, my code's blocked. But a few milliseconds later, the database is going to get back to us. And it's going to resume a promise in JavaScript. And so the runtime is going to resume the suspension. And what that is that's a special way of calling the button one click function, but saying, actually, I'm asking you to resume from here, from this suspension. And so button one click restores its local variables, restores its temporaries, jumps back to the right point in the function, and resumes its inner suspension, which restores its locals, restores its temporaries, jumps to the right place in the get function, and resumes the innermost suspension. And of course, that then returns immediately because it's now got the data. And so we have reconstructed our call stack, and we are now back to executing normally. And so that is how the Sculpt compiler turns idiomatic blocking Python into non-blocking JavaScript without making people deal with promises or async await. If you want to know more about Sculpt, check out sculpt.org. I am one of the maintainers, and we are always looking for more contributions. There's a bunch of really fascinating stuff going on right now with Python in the web browser. Please do come and join in. All right, so we've talked about compiling Python to JavaScript. Let's talk about something else you saw there, which is the way I was making function calls between the client and the server, which is, actually a fairly big deal. I may have been making a function call like this, but it really did look like a Python function call. It's got arguments, positional arguments, it's got keyword arguments, it's got return values. And how this is actually implemented is an RPC remote procedure call system over WebSockets. And the argument and return values are encoded as JSON, which is fine for simple values like you're seeing here. But what about non-JSON data? Like, for example, database rows. You saw me tossing around, lazy database iterators and rows from the database, and those are definitely objects that are not just JSON. So how do we do it? Well, the Anvil framework supports something called portable classes. So you can write a class in code that you can import from both client and server. So if you define a module on the client side in Anvil, you can also import it from the server, so you can see it in both places. And if you tag this class, anvil.server.portableClass, what that does is it tells the serialization machinery that when you when you pass one of these things as an argument into Anvil server call, or when you return it from a server callable function, it says it's okay to send one of these between client and server. And the default behavior is that it will store that you are sending an instance of class potato from module vegetables, and it will send all the instance variables, the class dictionary, along with that. And then it will reconstitute it on the other end and produce out the other end an instance of the potato class. If you want to be fancy, you can, of course, control how the serialization happens. So if you define a dunder serialize and a dunder deserialize function, you can control how this object is represented on the wire, and you can do some, there's also global data, so you can do some fun deduplication and global caching. And this enables us to create a pretty powerful system for transmitting arbitrary data like database rows. But that's only half of the challenge. Because just because I returned a row from the database to the client, remember the client in the web browser, that's untrusted code. Just because I returned a row from the database to that code doesn't mean I want it to be able to access any row in my database. So as we pass these rows from the database to the server, to the client, and the client effectively calls methods on that object. In this case, it's the done-to-get-item method for square bracket lookups, calling methods on that object. We need to control which objects they can call those methods on. And for this, we use something called a capability model, which is they can be described rather technically as an unforgeable token that carries permissions, or prosaically, if you've got it, you can use it. And so the idea here is that the act of passing an object to the client code gives the client code access to it. So intuitively, if we return those database rows to the client from the server function, well, that must give the client access to that data. So a capability contains identity, which database row does this object represent, and permissions, what is the client code allowed to do with it. And then the way we implement this is we take these things and we compute a digital signature over them using a secret key that is known only to the server. And so then when the client wants to perform some operation on this database row, it will pass the capability back along with the request. And the server will check that digital signature. And if the signature checks out, then the client must have been given access to the object with this identity with these permissions, because that's the only way they could get a valid signature over that identity and these permissions. So you can construct one of these objects yourself in code. This is what it looks like. So here I'm creating a capability scoped to the database with table ID 42, row number 12, and read-only access. And this is also something that you can be passed to and from Anvil server calls. And what this enables you to do is to do things like conditionally returning objects. So here, for example, we have a function called getPerson that checks whether the user is logged in using Anvil's built-in user management and authentication system, which I don't even have time to talk about today, but it's really cool. You should check it out. Checks whether the user is logged in, and only if the user is logged in does it return a row from the people table. And then your client code can get a row from that database and start calling methods on it. But only the rows that the server has chosen to return. And so line 21 of that server code implements a security boundary. We can be more clever. We can set permissions. So here we have a server function that returns a client-writable version of that row. So what it does, it takes a client-writable version of the people table and then searches that. And so the capability in the database row that's being returned will not be read-only, it will be read-write. And now we can get an object from the server and we can start updating it. And what this means is that we can do quite powerful things, because you can update the database from the client. You can update your database from your UI code. And suddenly, we no longer need to plumb every operation in our application all the way from the UI presentation down to the database and back, because everything is a Python object. And so we can just return, hey, here's a database row, and yes, you can edit it as a Python object. and everything gets simpler. We can be even cleverer than that. We can return views on tables, because tables themselves are portable objects. So here's the scenario. We have a set of records in a table, and they each of these has an owner, so it's linked to a row from the users table. And what we want to do is to enable the user code to access all rows that are owned by Meredydd at Anvil.works. And we can do this. So here's the code that does that. We get the current user, check that it's not none, check they're logged in, and we return a client writable view of the records table, but restricted to only rows where the owner column is the currently logged in user. And what that returns is an object that acts like a data table. We can add rows to it, we can search it, we can delete data from it. But in the capability covered by that digital signature is the restriction that the only rows that you are allowed to touch, the only rows you are allowed to create, the only rows you are allowed to delete, are rows where the owner column refers to this user record. And so you can push an enormous amount of computation out to the client by just passing Python objects around. So that is how we make function calls from the client to server and use capabilities to pass live objects around so that we don't have to mash everything into JSON. We can actually delegate access to whole views on our data tables to the client code. So the final thing I'm going to talk about is something is part of the editor you just saw me using. The first 3 points have been part of sort of Anvil, the framework. I'd like to finish by talking a little bit about the dev tool you just saw me using, and specifically its autocompleter. Autocompletion in code is really important. It gives you discoverability. It lets you see, for example, what methods are available on an object without having to go searching through the API documentation every time. It gives you speed because you can just hit a few characters and then hit the tab key and complete the rest. It gives you confidence that what you're doing is right because there are whole classes of bugs you can find and fix without ever hitting the run button because the autocompleter is giving you feedback. And for all these reasons, it just makes you feel good to use. It keeps you in the flow state. Now, these days, this is pushing an open door because most people, I imagine, are using PyCharm or VS Code. But if you are one of the people who is still out there holding the torch for Vim, you too can have autocompletion. If you haven't tried Jedi, which you can get as a plugin to Vim, I really, really urge you to give it a go, because it will change your life. If you're one of the few people who is not yet using autocompletion, join the party. Just do it for me as a favor. Try it for a week. You'll be amazed. Unfortunately, the existence of open source software like tools like Jedi doesn't actually solve our problem, because for two reasons. One is that Anvil is a full stack framework. And so your autocompleter needs to know about your database and about your server code and about what you've dragged and dropped into your UI. But okay, fine. Well, we probably could have patched that into Jedi. The more critical issue is that Anvil's editor is web-based. And when you're hitting the tab key, you're in the middle of writing code, there is just not enough time to go back to the server, parse all the code, run a code completion engine, send the results back to the client, and then autocomplete. You do not have 200 milliseconds if you are writing code. You're hitting keys too fast. If you've ever used a system that does server-side autocomplete, like Replit, for example, if you've used that, a very cool system in many other ways, but its autocompletion goes via the server, which means that it's a few hundred milliseconds behind and it completely ruins your flow. So we couldn't do that. We didn't have enough time. So we had to write our own autocompleter in JavaScript, which would be a fairly challenging thing to attempt. But conveniently, we have a Python to JavaScript compiler knocking around. Already seen how we can use the front end of that compiler to produce an abstract syntax tree. And that's exactly what we do. So when you are in the Anvil editor and you hit the tab key, we replace the place where your cursor is with a random symbol, and then we feed the whole module you're editing to the sculpt parser, and it will produce an abstract syntax tree. And at this point, it's actually fairly straightforward to walk over that AST and build up a representation of what's going on in your code. So here we would walk in to, we're executing a function called button one click. Well, it's got arguments called self and event args. So I guess those are local variables now. We've got an assignment. We're assigning to a variable called x. So, okay, well, we now have a variable called x available locally. We're doing a function call. We're calling a print function. Our argument is the variable named cursor. Wait, we just found our cursor. Well, okay, autocompletions, what's available? Well, we know what variables are available at this point in our code. And so we can sensibly offer them for autocomplete. Now, obviously, which variables are in scope is not the only thing you can work out if you're walking over an AST like this. We can actually autocomplete an awful lot about objects. So, and we're not restricted to local variables. Here we are offering as autocomplete the columns in a database row. But to work out what table that row came from, we actually had to walk over what type do you get if you take app tables and get the user's attribute from it. What type do you get if you get the search attribute from that? What type do you get if you call that as a function? What type do you get if you iterate over the result? And then what options are available as items on that row type? Which is absolutely fine, because all you do, you can recursively follow the AST, and that actually all falls out really rather nicely. We can autocomplete not just within a module like this, but between them. In fact, between client and server. So, for example, when the autocompleter parses a call like this, it notices, hey, I'm calling an Anvil.server.call on a function called sayHello, and these are the types of its arguments. And later, when we are parsing some server-side code, we can see, aha, we are parsing a server function called sayHello. And I know what arguments that gets called with. And so we can say, okay, well, D is actually of this type, which is this, this dictionary literal. And then we stick that into the local scope where it autocompletes. This allows us to autocomplete between client and server, between modules, between elements of our UI. We can autocomplete really quite a lot about Python objects, which leads to a sort of philosophical question about what exactly a type is. I keep using that word. And we could say, well, okay, in Python, the type of an object is its class. And, well, maybe, except Python is really dynamic. You can add extra attributes onto individual instances of a class all the time. Heck, sometimes you even have things that are different instances of a class we want to autocomplete separately. These two variables both contain instances of the dictionary object, but we want to preserve the difference for autocomplete. So what we do is we duck type our autocompleter. We say, sort of forget about the class. As far as we're concerned, these two variables contain two different types. Obviously, they share a lot of implementation, but they contain two different types with two different sets of items. So we track them separately, which means that when you autocomplete the square brackets in one, we can offer you more specific help. Okay. So I've shown you Anvil in action. I have walked you through how some of it works behind the scenes, and I'm just going to finish off by talking about some of the design philosophy underlying what you just saw. There are two big principles, and the first one is that code is good. We are telling a computer what to do. We've been telling computers what to do for about 3/4 of a century by now, and nobody has yet come up with a better way than text in a programming language. Periodically, somebody will come along and say, oh, hey, that's all too complicated. Here, drag and drop, use this flowcharty thing. And that is a false promise. Because ultimately, if you are telling a computer what to do, you're going to have to think like a programmer. And if you're using a tool that doesn't let you write code or tries to avoid writing code, you're either going to run up against a wall and want to do something that this tool doesn't support, or you're going to be tangled with Cthulhu's own flowchart and desperately wish you were writing the five-line for loop. So get me to the code. Write the 5-line for loop. It'll be easier. Even in the user interface, you saw when I was formatting that list of dates, I wasn't dragging and dropping some visual noodle from the database onto the UI designer. No, I wrote a Python expression. And because I was writing a Python expression, I could use the datetime library. Because all that facility was there, it would have been so much harder to build that with a no-code system. But if you get you to the code is good. The second and the most important big principle is accessibility. And if I did a straw poll in the chat right now and asked what accessibility meant, I would probably get answers like, well, it's about being simple enough for a novice to use. And you wouldn't be wrong. It's important to be accessible to novices. Frankly, it's embarrassing as a profession that the app delivery platform of our time, the web, the greatest system like that we've ever built, requires you to learn 5 different programming languages and 5 different frameworks to get it off the ground. Come off it. It's a little bit silly. So yes, absolutely, it is ridiculous that the web isn't simple enough for novices to use, and so we need to go fix that. But that's not enough, because if your only design constraint is this must be simple enough for novices, then you've created a playpen for the kiddies. And this does a disservice to the novices, because today's novice is tomorrow's intermediate programmer, is next year's advanced programmer, and you need to give them room to grow their powers. But the other group of people it's doing a disservice to are the experienced professionals, because just because I can write 5 different programming languages doesn't mean I want to. And it doesn't mean that anybody else wants to wait for me to deal with all that complexity when they're waiting for me to deliver something. So to be properly accessible, you can't just be simple enough for novices. You also have to be powerful enough for the seasoned pros. And some of you may be nodding and going, yes, yes, Meredydd, that's all very nice in theory, but these are incompatible goals. You can't build something that's that simple and that powerful. And I would like you to check yourself and look at your text editor. What language are you writing? We are here, virtually in my case, because we use the Python language. And Python is the first thing you will show an 8-year-old in their first coding lesson. And it's what runs Instagram. It is possible to be simple enough for novices and powerful enough for seasoned professionals. We are sitting on living proof of it. And it is only the garbage fire of modern web development that ever makes us doubt it. Thank you very much.